Thanks for everyone's time today. Andrew and I are really excited to have some moments of your time. As Drake mentioned, we were slated to give this talk a number of months ago, and now we're all really familiar with the virtual platform for giving presentations. It's going to be really hard to give a presentation in person when we all have to do that again. We're so used to being able to speak at our webcams. But let's see, Andrew is a Vice President of Water Resources at Wright Water Engineers. He's been here for over 20 years. He heads a lot of our post-fire work, and it's really fun working under him. We've worked in Southern California quite a bit and along the West Coast, and certainly some work in Colorado. And I've been at Wright Water for about 5 years. I'm from Northern California. I've lived in very fire-prone areas for much of my life. And my work at Wright Water, a lot of it revolves around post-fire hydrologic risk assessments and thinking more about geomorphic hazards. And also my PhD work. I'm a PhD candidate, as Drake mentioned, and my focus at Mines is on post-fire evapotranspiration rate changes and thinking about watershed treatments that we can use to help reduce post-fire exacerbated runoff and erosion rates. So really relevant topic, and it's hard not knowing the acumen of our audience, how far into depth we should go on to what are the post-fire hazards versus what did we do specifically for Pitkin County. So I'll just start out the talk by saying that the goal here is to talk in the context of a project that we did for Pitkin County, and the results are very relevant, but we're more so going to focus on the process that we used for this Pitkin County approach, because it's replicable and relevant to other communities that might be thinking about what they can do before a fire event to maybe get their hands around the problem before a burn occurs. So to get started, our overview today, we're going to talk a little bit about post-fire hydrology and from an engineering and scientific perspective. I won't go into too much detail, but I'll give you a resource or two to look at if you're interested in further information about changes conferred to the landscape during a burn. And then the project motivation that Pitkin County had when they approached Wright Water Engineers to undertake this study. Andrew will talk through approach and methods that we're using for Pitkin County. And this was a study that we conducted in 2019. We issued a final report to Pitkin County in February 2020, earlier this year. And of course, I'll walk you through results there and how those results can be extrapolated to other watersheds that weren't included in the study. And then I'm going to go over some additional resources that you can use in your area. So data sets that are published by maybe state or federal agencies that can be rolled forward into analyses for your particular set of site conditions if you experience a fire. So let's first dive into wildfires, the risk that they pose to downstream areas. And this is a photo on the left of a steep burn catchment in Southern California. This is the San Ynez mountain range, and this was after the Thomas fire. And you can see denudation of the hill slopes. And I know that these are topics that many of us are quite familiar with, right? Fire increases, runoff and erosion, but let's talk briefly about why, because it's relevant to how we parameterize hydrologic models, for example. So here you can see rilling and gulling and quite a bit of sediment accumulated at the bottom of a channel. So when we think about wildfires and post-wildfire risk, we are going to think in terms of human health and safety. So how are humans inhabiting the landscapes in the burn area and then certainly downstream of burn areas? And how is our use of that landscape going to be or should be changed or altered after a fire to compensate for some of the risk that's now posed? Structures that can include homes and businesses. And on the bottom right, this is a home also in Southern California after a devastating debris flow. And you can see velocities were high enough to bring really big size woody debris down and boulders. We had boulders the size of buses in this particular event. So thinking about where the structures are in the landscape in proximity to water channels and in floodplains. Infrastructure, so thinking about what in the burn area and again downstream of burned areas, what types of utilities are running through that area? Is there drinking water supply, reservoirs, or even channels that might be implicated by the fire? We will certainly think in terms of water quality, right? We're from a firm called Wright Water Engineers, so we're often thinking about how do channels and reservoirs, how is their receiving water impacted from a fire? And that's not the focus of today's talk, but there are a lot of resources out there thinking about water quality and disinfection byproducts. And I've seen a lot of webinars this year just on that topic. Environmental resources, certainly something we're thinking about in terms of fire. We can think about environmental resources as commodities. What are the ecosystem services that an environmental ecosystem can do for us? So thinking about, is your riparian corridor burned that used to filter contaminants or nutrients out of runoff? There's also, of course, the inherent and intrinsic beauty that's conferred by the landscape, and we can think about that too. And that's where wildfires become kind of a tricky topic. If Stephen Pine is a really great author, Pyne, that many of you are probably familiar with. I've read a number of Stephen Pine's books, and he's an historian. He's probably one of the world's leading experts about what role fires played in our landscape, how fire shapes our ecosystems, and the resources that humans interact with and depend on. And fire has been on the landscape for over 350 million years. A lot of our vegetative species in North America have evolved alongside fire. Certainly tribal communities used fire in ways to help manage their landscape for certain objectives. So fire is something that we can't always think about it as a bad thing, but as how can we work with fire and the way that fire will naturally present itself on the landscape and then reduce risks in the more fire-prone areas. And then cultural resources, not the focus of this talk either, but certainly something to think about. And one last thing I'll say about environmental resources, threatened and endangered species. So thinking about what is inhabiting the landscape that burned, or maybe in the receiving waters, if you're gonna have a much higher sediment load that's gonna run down into a channel with T&E species. Okay, so factors that affect post-fire runoff and erosion. And one of the easiest things to do first after a fire happens is to just look upwards. And if you are in a hilly area with high relief, thinking about topographic slope and aspect is certainly important. So here's a picture on the bottom left of a burned convex slope, and thinking about whether you may have steep slopes, and the steeper the slope, you may have a more magnified hydrologic and sedimentologic response after a wildfire. But thinking about the shape of the slopes above a value at risk is certainly important. Water, as you remove vegetation, you will expose soil grains to rain splash erosion and the erosivity of a rainfall event, more so with less interception. But when you have convex slopes, then you will start channelizing runoff faster. And we are concerned certainly about sediment loads that are generated during sheetrock erosion, but it's really when you start channelizing flow with ephemeral rills that will eventually become perennial gullies that you start adding to your sediment load. And that's where we really start seeing problems. So thinking about the shape of the landscape above you. And then aspect is really important as well. So us in the Northern Hemisphere, and the more northerly you get, the bigger the difference is with the amount of solar radiation that's delivered to southern facing aspect, where north facing aspects would receive much less solar radiation. And so we can think about this in terms of how does that shape the vegetation composition on a north facing versus a south facing slope. You might have in the Rocky Mountains more conifers and bigger tree species on north facing slopes. Soil moisture would certainly be quite different on north and south facing slopes. So you have to think about aspects when trying to categorize and quantify risks posed to you. And then interestingly, aspect would certainly play less of a role if you have less steep slopes. So you can be in a north and south facing hill, but if the hill is not steep, then the difference in solar radiation on each aspect would be much more muted. And then lastly, evapotranspiration. I could talk about ET for a long time, so I won't, but ET is really important. How does ET change after a fire? And that would also be quite driven by solar radiation delivery, because solar radiation and shortwave incoming radiation is driving the surface energy balance and latent heat of vaporization that's driving the ET process in conjunction with available soil moisture. So thinking about this topographic slope and aspect part of the equation, how does that actually affect the hydrologic processes of your landscape? We might see more rapid times of concentration. So the steeper the slopes and perhaps the more convex, the quicker your runoff rates may be. Lower thresholds for runoff as you remove vegetation, then you will reduce surface roughness. So thinking about Manning's equation, a lower N might mean more runoff. Well, I should say that that's more to do with velocity. But thinking about changes to soil hydraulic properties during the fire, we may have reduced infiltration rates, and I'm going to talk about hydrophobicity in just a moment, but that would certainly increase or lower your threshold for runoff. Hortonian overland flow might occur much more quickly if water is not infiltrating into your soils as readily. Increased runoff rates and volumes, commensurate increased erosion. So during a burn, you may actually have changes to your soil and mineral properties that reduce the resistance to the shear stress invoked by runoff. So you could not only have more erosion, but your shear stress required to detach sediment grains may be lower after a fire. And then potential for slope failures. This becomes really important thinking about landslides and how does the potential for colluvial material to come down in the Pacific Northwest, where infiltration rates are naturally higher, but we still see slope failures in many other parts of the United States. And that's a risk that can persist for a long time, not just immediately after a fire, but we might see slope failure increases for many years after a fire in areas with higher infiltration rates. And then difficulties to treat. Steeper landscapes may be more difficult to stabilize. You might need to use a bonded fiber matrix in your hydromulch. So these are all factors to consider. Let's see, 12:15, I'm gonna hurry up here. Other factors that affect post-fire runoff and erosion, thinking about your pre-fire vegetation type, the fire intensity and resultant burn severity, vegetation mortality, and changes to soil hydraulic properties and soil wettability. All of these factors come into play when thinking about how the hydrologic processes may have been altered during the burn. So hydrophobicity is the coating of soil grains by vaporized hydrophobic waxy materials in plants that will follow a temperature gradient down into the soil. And during the fire, right, those compounds vaporize. And then after a fire, at some depth below the soil surface, you start to coat soil grains. And so infiltration rates reduce. And that's a function of what is the type of vegetation that's on the landscape before the fire, right? So conifers tend to have more waxy materials and saps. Even chamise in the southwestern United States has a lot of waxy materials in their leaves. Not as relevant to us in Colorado, but again, it's really important to think about what are the species that are colonizing your landscape before the fire, so you can start to predict what your hydrophobicity might be like after a fire. And that would also be a function of fire intensity, how much energy is the fire expending, how hot is the fire getting, and then resultant burn severity, how altered are your soils. And these are all things that are looked at closely by federal teams and sometimes state teams. We have CAL FIRE and WIRT in California, for example. They might try to characterize and quantify these changes after a fire. And that's data that we're going to go over that we can use as engineers and hydrologists and even as natural resource managers in the community. So all of these changes may affect the duff and interception, well, the interception of rainwater and the storage of water in the duff and litter layers. So when you remove duff, then you are having less absorption of water during a rainfall event. You might again be forming hydrophobic layers, destructing soil biota, And when we think about water quality, it's really important to think about, well, what's happening in my watershed before waters either come into the channel or in the riparian zone or even aquatic biota in the channel. And are we destructing the microbes that transform ammonia to nitrates, for example? You might see a shift in the nitrogen species that is being delivered to your water treatment plants immediately after a fire as your soil biota recover. Increased sediment availability, decreased infiltration, and increased runoff. So let's talk for just a minute about hydrophobicity and what's happening. And we talked about this already, but when we combust litter that's on the soil surface, not so much in the tree canopies, right? Because we have canopy fires called crown fires. But when we have ground fires and subsurface fires, then we're combusting that organic material. And that also includes organic material in soils. So what is the definition of a soil? It's mineral, water, air, and organic material. Organic material and those upper horizons can comprise a significant volume of your soil. So all of these will play into hydrophobicity, and we're vaporizing those organic substances, condensing them under the mineral soil surface, and then coating and bonding to soil mineral particles. And hydrophobicity can persist for months to sometimes years after a fire. And the breakup of a hydrophobic layer can be dynamic. It can be from growing of plant roots. It could be from frost thaw heave cycles, right? But we've found the research will show that the shorter the fire return interval, the more persistent a hydrophobic layer may be. I just read a paper on that. That's quite interesting. So that then gets into fire regimes and thinking about how often does your particular landscape burn. And then we talked a bit about this, but duff layer, ash thickness, and soil sealing. So not only do we have decreased soil wettability after fire, but you may have some sealing of your soil surface. So during rainfall events, those exposed soil particles may be detached from a clod of soil, and then those fines may go and clog soil pores in the surrounding area. So you can clog your soil surface from other soil particles, or the ash that's been deposited during the fire event may serve to seal the surface as well. So all important things, and these are some pretty cool pictures. But as my colleague Andrew noted, he made this slide, a partially intact duff layer helps mitigate the magnification of post-fire runoff, and the ash layer can also absorb some small low-intensity rainfall, but washes away in more intense events. So in some cases, ash can also serve to be a bit of a protective layer until it burns off. And this is just a picture I include thinking about what a fire looks like downstream. This is in Southern California, and this is the lateral extent of a infamous debris flow that occurred. And we saw multiple fatalities. We saw multiple structures, many millions of dollars worth of damages. And this was due to a fire that occurred, intense fire, certainly a mosaic burn of soil burn severities, but then structures in the floodplain and close to a channel that doesn't run very frequently. They were ephemeral channels. And so it's easy to become complacent and to forget that there's a risk, even if you're possibly living on an alluvial fan type of environment. Some other kind of dramatic pictures. I know we've all seen photos of destructed homes after fires. But velocities can be so high that you might even rip a whole structure off of its foundation, which can be quite devastating. And then thinking from the water supply perspective, what's happening with reservoirs, very relevant to the Rocky Mountains, right? Denver Water has so many reservoirs that are pocked all throughout the Rocky Mountains in the backcountry, and they have significant expenditures after fires sometimes to remove and dredge sediment from reservoirs that has been deposited. So thinking about Colorado specifically in the wildland-urban interface, this is a figure, I'm sorry it's so grainy, but from 2010 that's showing the wildland-urban interface and then the intermix. 40% of our population back in 2010 was living in the wildland-urban interface, and the WUI is particularly vulnerable to wildfire risk because it's harder to well, these are areas that abut backcountry. So it's harder to treat the areas that surround structures in the WUI. There may be a lot more surface area that's backing up to a backcountry area, and we can't necessarily let a fire burn and remove a big fuel inventory, even if a fire is lit in the off season. So when fire weather may be more conducive to lower severity burns when we have homes at risk. So it's harder to defend the WUI, and that's a bigger problem that we can cover today. All right, so let's move into the Pitkin County study specifically. Why did Pitkin approach Wright Water? And I know that we have at least one or two Pitkin people on the line. It was Catherine Christoph that we were working with, and Catherine used to be a Wright Water employee. She was really lovely to work with during this study. So Catherine and others at Pitkin County approached Wright Water after the Lake Christine fire in July 2018. And that was an event that kind of straddled Pitkin County and Eagle County. And I think it raised awareness within Pitkin that, hey, we are vulnerable. We have a lot of values at risk in fire-prone areas. And what can we do to plan ahead before a fire? Pitkin County and Eagle County, they have a unique landscape in that much of their wildland-urban interface is right along the Roaring Fork Valley and the Roaring Fork River. And so they're quite aware that post-fire hydrologic risks specifically can be quite problematic if they don't plan for them ahead of time. And it's a simple first step to be 2 or 3 steps ahead. So being progressive and quantifying potential risk before the fire occurs could be quite helpful. And thinking about how our environment is changing on the global scale with climate change, increased climate variability, we may be seeing longer drought cycles, lower soil moisture, and higher accumulation of what we might call 1-hour fuels, highly flammable fuels. So what our fire risk looked like in the past may not be what our fire risk looks like in the future. Also a worthy reason to plan ahead of time. And then let's see, recent development of tools that enable rapid assessment of post-fire debris flow rates, volumes, and probabilities. So we have the capabilities now to think about what might our peak flow rates and volumes look like after a fire. We can do that before a fire, so why not get out ahead of the problem? So we all know where Pitkin County is. It's where Aspen and Snowmass Village lie, and Pitkin County helped us select 7 watersheds to include in our 2019-2020 study. And I'll go over what makes each of these watersheds unique in just a moment. But the point here is you cannot study your entire at-risk area. It would be much more cost-effective to select watersheds that represent the range of vulnerabilities that you might that you're going to come across during a fire. So representing the range of landscape conditions that may burn, and then representing and capturing your potential values at risk should a fire occur was what was behind the selection of these specific watersheds. And so I'm just going to run through these really quickly, but Castle Creek 1, we had 7 watersheds. And why did we select this particular one? This is an area where Castle Creek 1 is located, where there's a population that's at risk of being isolated from emergency services. So if we had a mud flood or a debris flow that occurred after a fire and it took out or closed down part of a highway, then we may have a significant number of people that have no access to emergency services. So that's a good reason to quantify what's happening in this area after a fire. This was an interesting watershed too, because there was a sister watershed right next to it, Castle Creek South, that we could compare and contrast what's happening with the landscape that is driving the response, because the southerly land or watershed was quite a bit larger than Castle Creek 1 North. So comparing and contrasting results with a neighboring watershed can be quite powerful, and thinking about the effects of variables such as area has. And then representative of similar watersheds, we selected Castle Creek 1 because it has similar vegetation, geology, and some other characteristics to a lot of the other areas in Pitkin County they were concerned with. Very similar for Castle Creek 2. And notably, Castle Creek 2 is located just above the city of Aspen, one of City of Aspen's major municipal drinking water intake points. So that's certainly very important when thinking about fires. Where are our water supply intake points? Is it more important to fortify the channel or the upstream areas or stabilize burn hill slopes above a water supply intake if you don't have a diversified water supply portfolio? So it's really important that you protect those one or two really valuable source areas should a burn occur. And one thing I'll note there is you can think about protection and stabilization of an area before and after a fire. So before a fire, it's expensive, and I'm not an expert in this, but there's the use of prescribed fire to lower fuel inventories, mechanical fuel thinning, and some other measures that can be taken to reduce the risk of ignition or reduce soil burn severities and fire intensities should ignition occur. And then of course there's stabilization treatments that you can do after a fire. And Crystal River, also very similar representative watersheds. And this, if a debris flow did occur here, it could cut off a major highway corridor. And notably, this watershed has experienced debris flows historically. So looking at past evidence of debris flows would also be quite important. I'm going to run through the rest of these because I'm just about out of my time. But the point here is, again, select watersheds that will give you a good idea of what you're dealing with should a fire occur. You want it to be highly transferable to other watersheds. So lastly, West Fork, this is a catchment area just above the Snowmass ski area, and its hydrology would be quite different from a more remote catchment. This has a lot of development at the bottom, so runoff might behave quite differently. And this was also our largest watershed evaluated. And Andrew is going to talk about the importance of area in just a moment. Let's see. Andrew, I think I'll let you take over at this point.
Great, thanks Natalie, and great job, and thank you for the great information. You know, I just like to reiterate what Natalie said. It's so nice to see so many familiar names on the participant list today, and I know Catherine Christoph is on with Pitkin County, who was really key to all of this work. It would not have happened without Catherine, so she has actually co-presented with me on this work before, and I just wanted to be sure to acknowledge her and GR and the others from Pitkin County who really made this happen. So thank you all, and also thanks to all the other folks who are on attending today for tuning in. So I'm going to talk a little bit now about the modeling approach and results. And you know, when we approach post-fire risk assessments, generally the more information that you have, the better. And this first reference I'm showing you here is a publication by the USDA NRCS on hydrologic analysis of post-wildfire conditions. This is an excellent starting point for doing post-fire hydrology, whether you're doing it on a watershed that has not burned yet and you're doing it hypothetically, like we did for Pitkin County, or if you're going out and trying to do it after a fire. This is a great reference that just came out a few years ago. Can you click it, Natalie, to pull up the next thing? Oh, I thought there should be 3 images on that slide. Is there like a click between the slides? Or yeah. And then the second thing that we're showing there is an example of USGS debris flow probability mapping. You know, that is not done for every fire, but USGS has developed some pretty robust regression equations that they can apply for real rapid assessment after fires. And that can also be done because the papers are published just with data on your own if it's for a fire that the USGS is not evaluating. And then finally, you know, we rely on a lot of these existing resources. You know, we really comb through the web and through other things to find all of the information that we can. But I've always found, and this goes back to the first fire I worked on, which was the Cerro Grande fire that affected Los Alamos, is that your professional judgment and past experience is extremely valuable. And of course, when I started working on Cerro Grande, you know, a year out of my PhD, I didn't have any experience, but I worked with Ken Wright, who had evaluated these things before. And we also worked with a former state geologist, John Rold, and I learned a lot from their experience. And then, of course, as you do these projects, you gain more and more new experience on your own. But you really want to factor in a lot of the available stuff and filter it through the lens of your experiences. And so now I'm going to move on to talking a little bit about model input, because we did a HEC HMS model. And I wanted to kind of walk through the different input parameters. And, as Natalie had mentioned, the most important thing about this presentation is the process, not the results. I mean, the results are important for Pitkin County, but the process is important for the rest of Colorado. And so we really always start with watershed data. Obviously there's some physical watershed parameters, things like area, land use, slope, types of vegetation and soils. And most of that information we usually get from local information. It's information that may be in the county GIS system or that can be obtained. You can also acquire LiDAR if you need to. And, increasingly there are capabilities to do LiDAR by drone, which can be a cost-effective way to do it compared to the cost of fixed wing LiDAR acquisition. You also need to have rainfall data, as the icon indicates at the bottom here. And typically there, we use NOAA Atlas 14 for point precipitation depths. And then we also use a local storm distribution, depending on what the local criteria are. But it's really important that you understand what events are most likely to cause mud or debris flows, because that can vary. Generally not in post-fire settings, but in non-fire settings and even in fire settings, you want to be sure you're using the right storm, and probably actually a range of storms of different frequencies to really represent the risk. And then other key parameters are related to curve numbers. You can certainly do modeling of post-fire effects using something like the Horton equation or other infiltration methods, but due to its simplicity and the history with which it's been applied to post-fire scenarios, the curve numbers are really a handy way, and there's a lot of literature on applying curve numbers for post-fire routing. And of course, you can calculate the lag time and the routing parameters. And, we always try to rely on published guidance, but, you always need to fit it to the unique conditions of the fire. And I'll also mention, and I'll mention this again in a few minutes, that the initial abstraction can be an important parameter to manipulate when you're doing this. Next slide, please, Natalie. Okay, so really what we did was pretty simple HEC HMS modeling. We're talking about models with anywhere from, 2 to maybe 8 subbasins. So not a lot of subbasins, but the modeling is really the easy part. Obviously, anybody can kind of turn the crank in HMS. It's really all about selecting the appropriate input parameters related to curve numbers, abstractions, lag time, and the precipitation that you're using. And the routing parameters are important to input too. And really what you have to keep in mind is that you're not necessarily trying to, represent every change in channel cross section as it changes along 1,000 foot or 2,000 or 3,000 foot routing reach. What you're really trying to do is to represent, find a representative section that represents the travel time through that reach. That's really what we're most interested in hydrologic modeling, is how these hydrographs combine together. So that's important. And then a final thing that's extremely important are using bulking factors. And that really takes clearwater modeling, which is something that HEC HMS can do. And we usually do this on the post-processing side, and builds in bulking factors, to account for the volume of the sediment and debris. And, in true debris flows, the bulking factor may bulk it by a factor of 2. So in other words, in a real debris flow, you could have as much mud, rocks, sediment, and tree limbs as you would water. And there is good published guidance on bulking factors, but you really have to think about it in the context of the specific watershed and source areas. So in terms of rainfall modeling, we used rainfall data from Pitkin County, from NOAA Atlas 14. We found the precipitation at the centroid of each of these watersheds. And then we used the rainfall distribution from the Aspen Urban Runoff Management Plan, which is the local criteria manual. And we actually helped to develop the Aspen URMP many years ago. And the thunderstorm in the Aspen UMRP is based on the CUHP 2-hour thunderstorm distribution. And back when we originally did the Aspen Urban Runoff Management Plan, we worked with Jim Guo of CU Denver to really look at rainfall distributions, to look at what data was available, and to determine what an appropriate distribution was for thunderstorms up in the Aspen area. And that was really what we came up with. So that is a very intense rainfall distribution, but it's also a good one because it's representative of the types of storms that will cause debris flows in post fires. And The other thing I'd just quickly note with regard to rainfall is usually when you use the USGS regression equations, or USGS comes in and studies a fire, they'll generate post-fire debris flow mapping on the basis of 25 millimeters per hour occurring over 15 minutes or 40 millimeters per hour over 15 minutes. And based on my experience in Colorado and others here at Wright Water, you know, a 1/4 inch in 15 minutes, which is basically that 25 millimeter per hour for 15-minute threshold on steep burn slopes, that will mobilize material. Now, USGS doesn't really evaluate larger thresholds because they're really just looking at what's initiating debris flows and causing them to happen. You know, some of the most severe damages can obviously come from much more intense rainfall events than that create very, very big debris flows. And keep in mind too, that when you look at the probability here, where we're listing these probabilities for rainfall, and I'll talk a little more about this, is that the probability associated with thresholds like 25 millimeters per hour over 15 minutes or 40 millimeters per hour for 15 minutes, you know, that represents a different frequency depending on where you're located. So in Pitkin County, that's one thing, and 25 millimeters per hour for 15 minutes is a pretty high threshold. But if you're at a lower altitude, it's not going to represent the same frequency of occurrence. Next slide, please, Natalie. In terms of, next slide. Go ahead and push the button to pull up the next. Yep, thank you. Oh, go back. Sorry about this, the difficulties. Yep, I just wanted to show them all at once. And so in terms of curve numbers, like I said, we did our initial parameterization based on guidance from the NRCS manual. And just like doing curve numbers for unburned watersheds, you know, that relates hydrologic soil groups A, B, C, and D to different types of cover. And what you can see in this table that's being displayed here, which is actually from this manual, and this was based on the Black Forest Fire and the West Fork Complex, that basically, depending on the type of pre-existing vegetation that was there and the burn severity, you can select a curve number for a burn scenario. And note that some of those get up into the 90s pretty fast when you get into C and D soils. So that's a lot of runoff. And, you know, typically you want to do this for both an unburned condition and a burn condition so that you're quantifying the magnitude of the changes. And, you know, if we do this proactively, like we did for Pitkin County, and we don't really know, was it a high burn, moderate burn, or low burn? Well, you can kind of bracket it by assuming, okay, well, it's somewhere between a moderate and a high burn would be a typical mosaic. And that's exactly what we did, since we don't know the exact fire characteristics when we're doing this proactively. Next slide, please, Natalie. So this slide touches on the bulking assumptions, and, you know, a lot of things go into bulking factors, and, you know, it's not just as simple as just picking a number out of thin air and applying it. And, you know, some of the different things that factor into bulking factors, you know, are related things like watershed size. You know, smaller watersheds tend to produce higher sediment concentrations because when you get into larger watersheds, there's more opportunity for depositional areas along the way. And, you know, slope also affects this. A very important factor is potential sources of sediment and debris within the watershed. You know, is there significant amounts of trees or limbs or rocks or boulders or things that are going to come down? So you really have to understand what's available there to be mobilized. And then, you know, also, and this relates to the watershed size and conveyance characteristics, you have to kind of think about a delivery ratio, because everything that comes off of a hill slope isn't necessarily going to make it down to the exact area you're evaluating. There's probably some deposition along the way. So all that is to say is that we kind of started out with some general numbers for the different types of flows we expected based on watersheds, sizes, and slopes, and you know, work on past fires. And then we kind of thought about these different factors and fine-tuned and adjusted them. You know, it's certainly not highly accurate, but if you put good engineering judgment into it, you can have well thought out assumptions that are good and provide you know, reasonable engineering estimates. Next slide, please, Natalie. So I'm going to just show really briefly on results, and I really don't want to get too wrapped up in the results here, because again, this presentation is more about the process than the results. But you know, what we're really showing here is you know, the results for a modeling. So we have Mudflow peak discharges, and those would be bulked numbers that we present. You know, and we do that for both unburned, moderate burn, and severe burn. And then we do the same thing, and we express them though in terms of unit peak discharges. And I'm a big fan of unit peak discharges, especially when you're doing peer review of hydrologic modeling, because it's a really good way to see between watersheds of different sizes just how things are stacking up. And you don't, I mean, obviously unit peak discharges do change with watershed size, as we would expect that they do, but it's also a good just kind of way to check numbers and see how things are changing. And then finally, you'll note on the far right-hand side that we have ratios of moderate to unburned and severe to unburned. And, you know, these are some pretty substantial ratios. You know, for those really frequent events, the 1 in the 2 year, where we list them as being undefined, that's because in this area, a 1 to 2 year event in a small watershed just doesn't produce much runoff, if any. And so really, you know, any increase is going to be infinite compared to nothing, right? We're dividing by 0. And you can see that the ratios become a little more modest when you get to higher events. You know, the couple of things I would note on this is just because the ratios are the highest from the small events, that's exactly what we expect, because the smallest events, you know, have a higher ratio of infiltration to precipitation. But those may not be the events that cause the most damages. You know, a lot of the big damaging events are when you get to flood events, like maybe a 5-year, 10-year, or even a 100-year event that occurs on a burned watershed. And then you could have some real serious problems. And, you know, at lower elevations, sometimes we don't see at the large events, like a 100-year event, ratios that are quite this high. But when you're talking about Pitkin County, you know, because they're at a higher elevation, the 100-year rainfall depth is not that much to begin with. And so there is in Pitkin County a fair amount of infiltration in these types of watersheds in a 100-year event. And when you take away that infiltration capability, you take away the vegetation, and you add a lot of soil that can be mobilized, that's why you can get some very high ratios here. Next slide, please, Natalie. Now, this is another way of showing what we just did. And we developed these plots. We developed some regression equations based on our modeling. And what this really shows is a plot with area on the horizontal axis and your peak discharge rate on your vertical axis. And this is for a 2-year event, but we developed curves like this for every frequency that we modeled. And we actually have quite a good polyline fit. I'll show you some comparisons with some other data in a minute. But, you know, in this case, to kind of geographic clustering of these watersheds where all of them have similar rainfall, they have similar slopes, they have fairly similar vegetation characteristics. You know, what we're able to do is to develop a pretty simple relationship between area and peak discharge. And, you know, you know, USGS has their regression equations, and they have a lot of other factors that go into it, like slopes, precipitation, and other things related to the runoff response. And, you know, those things did go into these curves too, but they were just done as a part of the modeling. And because they don't vary all that much, we can develop this extremely simple relationship. And, you know, because a lot of these factors are fairly homogeneous across the watersheds. And the beauty of this then is that if there's a fire in Pitkin County and Catherine or GR or anybody up there has to go out and they have infrastructure at risk and they want to know how big the flows might be, you know, they can just plug in the area, or they can go to these charts and they can say, okay, my watershed is 100 acres. It's a mosaic burn. Here's what my expected discharge is. And again, it's not an extremely precise number, but it's a good one for ballpark planning and for emergency responses. And so this really, you know, cuts out a lot of the work when there actually is a fire, because they can do some real quick estimates. And I again want to caution, this should not be used anywhere but Pitkin County, because it was developed with their unique watershed and precipitation characteristics. Next slide, please, Natalie. So we also did the same thing for volumes, and for the sake of time, you know, I'll kind of skim over this slide, but again, the story was very similar. You know, greatest increases for the smaller events, but even substantial increases at larger events. And I'll also just mention that across the bottom of these past 2 slides have been some pictures from our watersheds. You know, we went out and visited every one of these to really do this evaluation the right way. Next slide, please, Natalie. So to ground truth our modeling, we also made some comparisons to the burned area emergency response, or BAER, modeling that was done for the Lake Christine fire, just to see how what our model projections, you know, for the proactive planning would have compared when we compared it with an actual fire, an actual post-fire BAER assessment. And you can note here in this figure, you can kind of see at the bottom of this valley is basalt, and you can also see El Jebel. And this was a unique fire because most of the burn was in Eagle County, but there certainly were areas in Pitkin County along the Roaring Fork that were affected. Next slide, please. This shows you the comparison with the BAER results, and I'll be fairly brief about this because they lined up fairly well. What you can really see here, the BAER results are potted in blue, and down in that kind of sub 200 acre level, you know, Lake Christine was a mosaic fire, so it should be somewhere kind of between the bottom and the top curves. And indeed, it did line up fairly well down for the smaller watersheds. When we get to the larger watersheds, the BAER for Lake Christine was really following more along our moderate burn line. And there are two reasons that that could be due to. One of them is that there were moderate and low burned areas, and we didn't evaluate a low burn scenario. So that's probably part of it. The other part of the explanation is that we used a 2-hour storm and the BAER used a 1-hour storm. And again, we're only comparing this for the 10-year event because that is the only recurrence interval, I believe, that the BAER team evaluated, or at least the only one that they published. And so our regression equations stack up really favorably with the analysis that the BAER team did. And fortunately, we have those across a lot of different recurrence intervals, so it can be a quick and easy tool. Next slide, please. A few more things. We also wanted to make some comparisons with other studies that were done by the USGS. And I know we've talked a bit about the USGS debris flow equations, post-fire debris flow equations. You know, they've done work down in the West Fork complex near southwestern Colorado, and they did a really cool proactive planning study actually up near Lake Granby a few years ago. And so we used some of the regression equations in this report, and we tried to apply them just to see how our results would stack up against that. And next slide, please, Natalie. This one will win the award for the most confusing slide of the presentation. And since we only have 12 minutes left, I'm not going to explain it all. But this is really a complicated figure showing the comparison of our results, which are kind of the thin lines and the little dots, with some of the results using USGS regression equations, which are the thicker lines and the colored dots. And really the takeaway from this is that they don't agree well. You know, some of the USGS regression equations are based on only really a few points in Colorado. A lot of those equations were developed using data from Southern California, and they are very robust when you apply them down there. But in Colorado, at least at the elevation where Pitkin is, you know, there are enough differences between where the data collected for the regression equations from USGS have been developed and, you know, the lower precipitation, higher altitude characteristics in Pitkin County, that you really can't apply the USGS equations there. You know, I actually did apply them to a few of the basins in Lake Christine. And in some cases, I actually calculated, you know, higher volumes than would physically be possible given the rainfall amount. So, you know, an inch of rain, you know, and you plug it into the regression equation and it produces 4 inches of debris flow from the watershed. And we just know that can't be right, even with an extremely high bulking ratio. So the USGS regression equations are a great tool, but be cautious about applying them in other locations, especially if you're at high altitudes or places that vary significantly from where the equations were developed. Next slide. Very quickly, I want to touch on kind of how we use some of the results of this. You know, we did some 2D modeling in this case, just because we were really kind of just doing proof of concept. You know, we used HEC 2D with our bulked flows. You know, if you really want to explicitly model debris flows, something like Flow 2D is an excellent tool. That's actually what we used for the Aspen mud and debris flow study. But, and that could be a next step in some of these watersheds too, where it would be useful. But for proof of concept, we thought we could show the point fairly well for a quick, rapid assessment using HEC 2D. And we thought it worked fairly well. And it also helped to identify where you could do some fairly easy mitigation measures. Next slide. We also often like to talk to clients about, you know, the probability and to put risks and damages in the context of probabilities. And I always like to show the 2-year curve because we all know it's 50% in 1 year. But when you think in Colorado, your typical fire recovery period is probably going to be 5 to 10 years. You know, if you got to year 3, your probability of a 2-year event happening at least once is almost 90%. So in other words, in the fire recovery period that's typical of Colorado, you can plan on a 2-year event happening. And the next slide. We can also relate this to the conceptual hydrologic recovery curve, which is something that Jim Guo and I developed probably about 10 years ago on the 4 Mile fire. And again, these things can be adjusted to any specific fire, but it really shows that as you have the rising risk of probability, in this case for a 10-year event, you also have decreasing hydrologic risks over time. So really the key is to find that combination of risk, you know, and protection that you want, and, you know, to assess the right point in recovery. And oftentimes, you know, it's really not economically feasible to do much beyond a 2-year event. Next slide. We summarized Next slide. Summarized all this information in fact sheets, and fact sheets like this are really important because you need to communicate these results really clearly to emergency managers and sometimes to the public too. Next slide. And then finally, I showed this last slide. These can be extrapolated to other watersheds, especially in Pitkin County. And that's the great utility of this. If there's another fire, Pitkin County will be well prepared, at least for figuring out what potential discharges will be, because they have this work and they can go out to any area and in the space of about 5 minutes for any given basin determine what the flows should be. But these regression equations are not supposed to be used outside of Pitkin County. They're based on unique rainfall and watershed characteristics. However, this really provides a blueprint for things that could be done. I mean, this could be repeated easily in other locations in Colorado to develop locally specific curves to be prepared for post-fire runoff and debris flows. Now I'll give it back to Natalie. Thanks, Natalie. Sorry to leave you with such little time.
No, that was great. That was really the bulk of, I think, what was most important to convey to our audience. So I'll wrap up with 2 minutes. So we leave 5 minutes for questions on resources available to you during the, and most of these you'll be familiar with, but during the fire, data sets that you can easily access about what's happening and where burn perimeters are, and fire progression would of course be InsoWeb. We always go there first. That's government agency website. So we always visit InsoWeb during a fire when we want to get our hands around what estimated containment dates are. You can also get spatial data for fire perimeters, et cetera. During the fire, I always visit NIC, National Interagency Coordination Center, really good for figuring out what types of response teams are being deployed, if it's a type 1 or type 2 or type 3 incident, et cetera. So that might be more in the firefighting wheelhouse versus the post-fire engineering assessment, but certainly relevant if you're interested in fire. I also love looking at the fire MODIS maps and VERS. So this is something I use every day during fire season to look at where are our satellites picking up higher temperatures. So this is based on Planck constant and the fact that higher temperatures will actually have a more quick increase in wavelength frequency in the electromagnetic spectrum. So we can exploit that with remotely sensed data and hyperspectral and multispectral imagery. And that is super cool. So easily accessible to the public. And let's see, after the fire assessments, Andrew talked about BAER, but you might also look at what your state provides. In California, it'd be the Watershed Emergency Response Team. And this can get you a good sense for soil burn severity, vegetation mortality mapping, USGS debris flow probability models. I also use the Monitoring Trends and Burn Severity data set. MTBS is an interagency project. They map burn severity and fire perimeters using normalized burn ratios. So I've done a lot of work with MTBS data sets, and that's just a good data set. And then USGS StreamStats, we use StreamStats all the time, not just for fire projects, but anytime we want to get what's based on USGS regression equations, what are different interval return flows, easy way to delineate spatially drainage basins, et cetera. So this is what we use to delineate our subbasins for this Pitkin County study. And then you always want to think about where is flood inundation mapping putting water, even in unbolt scenarios. And we've seen examples of other fires where it was clear that emergency management didn't think about where those USGS debris flows that were, USGS is mapping high probability for a debris flow to occur, but where's the runout going to happen? And the first step you might do is look at your FEMA firm flood insurance rate map. And then if you want to get more involved, you can do something like apply two-dimensional hydraulic modeling like we did. And Andrew showed you that conceptual model. And then you can think about what are best management practices that can be prescribed to your particular set of landscape conditions to stabilize a burned environment. And just because of time, I don't have time to go into this, although I should have saved a minute to do that. So apologies, but let's leave the last 4 minutes to questions. Thanks so much for your time, and Drake will hand it over to you.
Yeah, thank you so much, Natalie.
Sorry, one thing I want to mention, because it's so important to understand the science and engineering behind what happens with your landscape. And we only had 10 minutes to go over that. One really great podcast, if anyone's interested, or excuse me, a YouTube video was hosted in Aspen and Carbondale by Liz Schackenberg. She's a hydrologist with the U.S. Forest Service. And there's a YouTube video if you just look up Liz Schackenberg. She's also a bear team coordinator for the state of Colorado. And that's a wonderful 1-hour presentation if you want to follow up today's information with that. Thanks, Drake.
No, thank you, Natalie. And thank you, Andrew. That was a great presentation. You know, unfortunately, this year we've really come to terms with the risk associated with a lot of these fires in Colorado. So developing kind of a methodology to understand the potential risk if and when a fire happens in your area, you know, those tools are really useful. I usually like starting out the questions with one of my own, but we have a lot of great questions from others here in limited time. So I'll just start reading off the questions from chat, and we'll probably run a little past the 1 p.m. time slot here for those who want to stay on and just get the input from our speakers here on this question. And we'll go through this fairly quickly. So Stephen Griffin asked the first question: is there a general guideline for post-fire debris flows regarding critical hillside channel slope to initiate a debris flow? 30, 25%, et cetera, for a given rock, mud, debris mixture?
Yeah, I'd be really glad to answer that. And unfortunately, there's not really a general guideline because it's really specific to the type of soils you have. I mean, certainly the steeper the soils are, the higher potential you have. And you know, and we see, you know, a lot of oversteeping slopes even. And, you know, if you see slopes that already have dry gravel before you have a fire, those are the ones that are going to be the highest risk. But, you know, it really depends on the burn severity and other things. And, you know, for the same slope, if you had a low burn severity versus a moderate burn severity, you know, the debris flow response off of that hill slope would probably be different. But you know, certainly lower sloped areas are lower risk, higher sloped areas are higher risks, but I'm not aware of any specific guidelines on that. Although it's a factor that goes into the USGS equations.
Great. So from Dana McClone, if it's a more severe burn, higher burn severity, does that mean the hydrophobic soils are deeper?
I can take that. That's a great question, and certainly something that, right, we talked about thinking about fire intensity and then resultant burn severity when thinking about what the changes conferred to the landscape are. So it is true that typically with higher temperatures and longer durations of high temperatures, then you may move that soil burn severity layer deeper, and that's because you have more heat energy to burn more litter and duff above a soil hydrophobic layer that's developed. And that is really important. One other thing I'll say, sorry, is that you can also get temperatures high enough to decimate a hydrophobic layer. So it's kind of a curve with temperature where, and duration really, where higher temperatures, longer durations, more and deeper hydrophobic soil layers, and then at some point you would eventually incinerate the hydrophobicity. So look at your soil burn severity mapping and think about that appropriately. But the deeper your hydrophobic soil layer, the more material you now have on top of it that's available for transport down gradient, just like a persistent slab with avalanches. The deeper the slab, sometimes the more dangerous the scenario, because you have all the more material atop that slab to slough off and be entrained in debris flow or mud flow.
Great. Yeah, no, I think that's a really important point, Natalie, and thanks for the question, Dana. Jennifer Keys asked, this presentation seems to support municipalities, state agencies, or federal agencies in purchasing land or easements up gradient from their drinking water sources, allowing more ease in using prescribed burns, mitigation, etc., ahead of fires as preventative measures. Many water supplies are located down gradient of Forest Service areas. I wonder if municipalities should find ways to better support Forest Service in mitigation efforts, given the benefit it has to their water supplies and lack of funding for the U.S. Forest Service.
One thing, Andrew, if I can say one thing and then I'll hand it over to you. We did not talk about how water suppliers and utilities can better hedge their, hedge against fire events. And that's really important. And I shouldn't speak for Denver Water, but just doing a little bit of research in Denver Water, because they're a really good case study. Denver Water has so much area that's part of their source area, especially for the upper Platte River supply source area. And so what they've done is, first they've developed source area protection programs, but they've also developed relationships with federal agencies like Forest Service with the Forest to Faucets program, where both entities, where the water supplier and the agency, and then they get Colorado Geological Survey and maybe some other agencies involved, where they all set money aside for performing fuel reduction treatments. And it's a good way to energize everyone to move together towards a common goal. So there is example of how do we get both sides working together, especially because water municipalities, the bigger they are, the less ownership they'll have over their source area, right? Denver Water doesn't own all the area that they have a stake in protecting. And so getting collaborative relationships and partnerships going is a really good way to get a facilitated response.
The only thing I would add to that is that one of those USGS studies I showed actually was a study that Denver Water participated in, which was looking at risks to, I believe it was Lake Granby, assuming make-believe fires, just like me and Natalie did. So they're definitely thinking about that, and it's a really big deal issue, because not only can fires affect reservoirs, they affect your treatment costs with ash and fine sediments. There's also some new research that shows that when fires heat plastic pipes, they can leach out benzene and all sorts of other nasty stuff for months, if not years to come. So the water supply impacts of fires is a really, really big deal. And I think we're lucky, at least those of us who live in Denver, that Denver Water has such an extensive program right now.
And other things we've seen, like was Durango or Fort Collins, right after the 4 Mile or the Hayman fire. They're a smaller utility, so they have a much more discrete area that they're more in danger of having the entire area burn than Denver Water, where there's never going to be a fire season that burns all of DW's source area. But what Fort Collins does is they have an alternate water supply, right? So if you can't diversify your water supply portfolio, then you should have contingency plan in place. And we're not issuing guidance, just learning from what we've seen others do and what's worked and what hasn't. But being able to, if you have to shut off your intakes for your major water supply, well, good to have a backup emergency source in that event.
Mm-hmm. That was something that was relevant here in Glenwood Springs with the Grizzly Creek fire, as that was burning upstream of one of the city's intakes. So those are really important considerations. We have 2 more really good questions from Stephen Griffin, and I'll kind of combine them here. The first, if you have a post-fire condition that you're attempting to analyze via a rainfall runoff model, how might you calibrate your initial abstraction? Is there a way to take on-the-ground infiltration test to transform that into a revised initial abstraction? And then regarding the 2D hydraulic modeling, was there anything that you pulled from to increase the viscosity or sludge factor of your flow?
Good. Well, I will take both of those, and those are good questions. And I'm sorry I didn't touch on the initial abstraction like I said I would when I was presenting. We were running out of time, but I'm glad you asked that question. The initial abstraction, which we usually use, is 20% of the storativity of the watershed. IE is 0.2S, and none of us usually think much about that. You just go and plug away and do it. You pick out the curve number, but usually most people don't think about adjusting the initial abstraction. And, I don't think on the ground infiltration measurements will really get you there, because really what the initial abstraction is representing is not infiltration. I mean, infiltration's in the curve number. What that initial abstraction is really representing is the interception that you would have from the canopy and the depression storage that would occur on the forest floor. So it's the 2 things that really happen before you get to the soil surface to cause to actually then get infiltration. And so really the way I think about it, 0.2S is just, that's the number everybody always uses. And so you really need to think about it from a process-based standpoint hydrologically. And what you need to do is say, okay, if this unburned watershed would typically have a 0.2 times your storativity for those types of losses, and now you no longer have needles, now you no longer have the duff layer, you're on a steep slope, so you don't really have meaningful depression storage. Well, you could very easily reduce that to 0.05 or 0.1. Just based on observations in the field of burned areas relative to unburned areas. So that is a helpful calibration tool, because, you know, when you have a 45-degree slope with nothing on it but burned charred material, you know, your IA might be nothing. And so anyway, so that's a valuable tool in the quiver. The second item, though, is related to the 2D modeling. And I actually want to give a shout out to our moderator here, Drake, because he's the guy that did the 2D modeling. But we did not, in this case, represent the increased viscosity. You know, I think I mentioned when I was presenting that if you really, you know, want to model that and you want to model the viscosity effects, you know, you really should be using something like Flow 2D that does explicitly model that, as opposed to HEC RAS 2D. You know, but if you need something that's a quick and easy screening tool, I mean, Drake here can get a HEC RAS 2D model up and running in about 2 hours. And so, you know, for at least initial, you know, figuring out where the water is going to go and what it might affect, you know, doing, you know, non-viscous flows in HEC RAS 2D, but using your bulked flows and you know, and the hydraulics are just like normal water, that will at least get you in the right ballpark. And it's something that can be done quickly and easily. So there certainly is much more sophisticated modeling that can be done. And one of the things I've always thought, and I'll say this as maybe a closing remark, is that, you know, when you're doing watershed plans and you're doing, you know, 100-year floodplains and you're doing drainage design and master planning and things, you know, if you are in a community that has watersheds that could potentially burn, you know, doing a burn scenario is easy. I mean, if you're already evaluating all the floodplains and all the hydrology, you know, it's just a matter of changing your curve numbers basically and making a few different assumptions. And, you know, we could have much more resilient maps if we were to do that. And I'd also just like to echo one comment that Katie Yacht made, which is related to the fluvial hazard zone mapping, which is something that she's helped a lot with, and it's a CWCB program. And that is also extremely valuable because that really defines erosional hazards in a lot of these runout paths. You know, so really understanding fluvial hazards and looking downstream is extremely important in these areas. And I think our closing message is that you don't have to wait for a fire to happen to do that.
Oh, I think that's great, Andrew. A great summary. And thanks again, Katie Yacht, for mentioning the fluvial hazard zone maps. If you all had tuned in for our previous presentation, Katie gave a great overview of kind of what goes into that methodology and how those maps are used. I think that kind of wraps it up for the questions here in the presentation. Thanks again, Natalie and Andrew, and thank you all for tuning in to these virtual webinars. I'm sorry, you know, we had originally scheduled this series to be an in-person event, but we had to go digital due to the COVID-19 circumstances, as many other events had to do this year. We're looking at our options for next year, so please stay tuned on what that'll look like. And just as a reminder, if you need the CFM certificates, we'll probably be processing those within the next week or so for those who have attended today's webinar. Thanks again for you all for attending, and thank you, Natalie and Andrew, for presenting. I thought that was a very insightful and timely presentation. So thanks everybody and have a great day.
Thanks, Drake.
Thanks all. Thanks for your time.